what am I, example 4? Here we go. A equals to, excuse me, 3 minus 4, 4, 0 minus 1, 4, 0, 0, 3. So let me tell you a little linear algebra fact. If A is triangular, so what triangular means is the shape of the matrix is either upper or lower triangular. So upper triangular looks like this. Lower triangular looks like this. So there's zeros over here and zeros over here, like that. So this is an upper triangular matrix. You can read the eigenvalues from the diagonal for such a matrix. I can look at this and I can say, then the eigenvalues are the diagonal entries. Now, of course, if you didn't know this fact, it wouldn't be a big deal. When you go to calculate the determinant of A minus lambda I, you will get 3 minus lambda, minus 1 minus lambda, and 3 minus lambda. So it'll be clear that the characteristic equation, I mean, it's almost immediately obvious that if you look at the determinant of A minus lambda I, you get 3 minus lambda, minus 1 minus lambda, and then 3 minus lambda. Anyway, the point is, we have, let's say, lambda 1 equals to minus 1, and we've got lambda 2 equals to 3 repeated. All right? Yep.
What are the rules for that triangle thing? Can you have zeros in the top at all, or no? Like in the upper? Could that negative 4 be a 0?
Yeah. Oh, yeah. Yeah, that could be whatever. For example, diagonal matrices this applies to.
But that 3 at the bottom right cannot be a 0. None of the ones on the diagonal can be a 0.
Diagonals could all be 0.
They can all be 0?
Yeah. The matrix with all zeros is both upper and lower triangular.
So then this one over here is 1, 1, 0.
Upper. This final one's upper triangular. Yeah. This one's neither, because it's got non-zero things above and below the diagonal. Oh, by the way, I can't write the matrix of solutions for my last example because why? I'm missing my third solution, right? I also can't write the general solution for the last example because I don't have enough. It's incomplete at the moment. We need something else that we're missing at the moment. Let's see here. So lambda 1 equals to minus 1. We should solve A plus I, right? U1 equals to 0, which is what? 4 minus 4, 4, 0, 0, 4. Ooh, I like that one. 0, 0, 4. So this time, look, this time, either one of these guys translates into 4 times W equals to 0, right? So apparently, W is 0, all right? And once you know that, it's easy to go back and use the first equation, right? What's the first equation say? U minus V plus W equals to 0, right? From first row, divided by 4, obviously, right? But W is 0, right? So U equals to V, right? So set V equals to 1 and get U1 equals to 1, 1, 0. What's my other eigenvalue? Lambda O equal to 3, right? So I should look at A minus 3I times U, let's say 2 equal to 0. What's that? Mm-hmm. Deja vu all over again, first and second row, right? Let's see, 0, 0, 0. Aha. Okay, so what we got? We got, again, my W is what? That's not right. W is not free, is it? What's these two top equations give me both that minus V plus W equals to 0, right? So therefore, V is equal to W in my solution. And what is U? I mean, this is a profound question. U is free, right? Sorry, I'm an idiot. So U2 is U V V, which we can rewrite as U times 1, 0, 0 plus V times 0, 1, 1. Congratulations, you just found the basis for the null space, whatever that means. But, of course, these are both lambda equals to 3 eigenvectors. And now I have enough information, I can write down the general solution. C1 e to the minus t 110 plus C2 e to the 3t 100 plus C3 e to the 3t 011. That's the general solution for this problem. You notice that there was a repeat of eigenvalue 3, but there's no t in this solution, right? This time, even though the eigenvalue was repeated, we found 2 eigenvectors, right? Over here, this example, we had the eigenvalue 3 repeated, but we only found 2 eigenvectors, right? If we can find as many eigenvectors, linearly independent speaking, as we have eigenvalues in the P of lambda, then it seems like we can find the general solution. And if we can't, we're missing something, like in example 3. So next class, I'll explain what it is we're missing and how we can find it, as well as cover the complex case, which I still haven't done. So sorry about that. But I figure it's better to do more examples, right? Oh, we still have a couple minutes. This door gets moving so much I think I'm over time, but I'm actually still 5 minutes left. Idiot. Let's see here. So what's an example which should need a t in the solution? Let's reverse engineer something, right? You guys are, your life, you're going to be working against the Chinese, right? Most likely. Some of your engineers, I mean, I figure your existence probably is to beat China at its own game, right? So reverse engineering is important. So an example we know that has t in it in a non-trivial sense is this one. Y prime prime plus 4y prime plus 4y equals to 0. See, this is coming from lambda squared plus 4 lambda plus 4, which is lambda plus 2 quantity squared equals to 0, right? And I know my solution set is y equals c1 e to the minus 2t plus c2t e to the minus 2t, right? And so if I do reduction of order on this, it must be that the corresponding system needs t's in the solution. So what's that look like? x1 equals to y, x2 equals to y prime is reduction of order here. See, then this will give me, what's this give me? This gives me x1 prime equals to what? x2, right? Yeah. And x2 prime is y prime prime, right? But what's y prime prime? So it's minus 4x1 minus 4x2. So apparently, if we look at this matrix problem, x1, x2 prime equals to 0, 1, minus 4, this thing must somehow suffer the same fate as my example 3. What's the, if we look at this A, what's the determinant of A minus lambda I here? Minus lambda 1 minus 4 minus lambda, which is what? Lambda squared plus 4 lambda plus 4, right? That's not surprising, is it? Same algebra. So lambda equals 2 twice, and if we look at a minus 2I u, what do we get? Is that the same equation? Wait a minute. I think I made a mistake here. Where did I make it? This has determinant 12 plus 4, which is 16. That's invertible. There's a mistake. 1 should be a 3. Where's that? The 1 should be a 3? Oh. Oh, I'm sorry. I'm confusing the root with the factor. It's just my own stupidity. So we're supposed to do plus 2i, right? That was the thing, because lambda equals to minus 2, right? Thank you, guys. So, okay, now those are the same equation. So you get, you get 2u plus v equals to 0. Therefore, we get u1 is, u minus 2u, or if you like, 1 minus 2, if we set u equal to 1. What's that?
That's when your classes are rooted.
Yeah, I guess so. But I mean, we're a minute over. It's very zealous. Very, really, really likes calculus 3, apparently. Anyway, the point is, we only get one eigenvector. As you can see, there should be 2, right? If you could track back, you could figure out what the solution is here from taking this and feeding it through the reduction, and you'd find something that has a t in the solution that's not an eigensolution, right? So we need to understand how to come to those, how to find those more systematically next time. But anyway, that's it, guys. So you can cut it off.